Good evening and happy Earth Day, everyone. Welcome to a new event for our Science Festival. My name is Irene Porro, and I am a director of the Krista McCullough Center. So I'm very happy to be the host this evening of an event, again, offered as part of the Framingham State University Science Festival that is called Science on State Street, Planet Earth Edition. Since April 12, the festival has featured more than 30 virtual events leading to today's celebration of Earth Day, with offerings for learners of all ages, background, and interests. However, all these presentations had something in common, which was, of course, a focus on planet Earth and how important it is to take care of this, our own planet. So before we start with this evening's presentation, just want to give a few reminders how we will coordinate the interaction with the audience. First of all, this is a Zoom webinar. What that means is that only the presenters will be visible on audio, will be visible on camera, and will have direct access to the audio. So you will be muted for the duration of the presentation. Right now, though, if you feel inclined to do so, feel free to share in the chat an introduction to yourself and maybe letting us know where you are joining us from. If you have questions during the presentation, we really would like you to use the Q&A feature on Zoom, located in the bottom right window of the Zoom window. So that will be a little bit easier for us to keep track of all the questions. We plan to answer them at the end of the presentation, but also be careful that maybe some of your questions, they may be answered as we go along during the talk. All right. So also, I shouldn't forget to remind everyone that this presentation is recorded. It's being recorded as we speak. And the recording of this presentation and of many of the events that we had done in the past week or so are going, and some already, but are going to be available on our website, the same website where you found the list of all our events. And I'm sure that someone is actually posting that website in the chat right now. So if you missed some of our previous events, or you would like to listen into this one again, just go to our website and find the link to the recording. All right, and now it's time to start tonight's program. Our guest today is Dr. Jeff Bennett. Jeff Bennett holds a degree in biophysics from the University of California at San Diego and a PhD in astrophysics from the University of Colorado Boulder. He specializes in mathematics and science education, writing for and speaking to audiences ranging from elementary school children to college faculty. Dr. Bennett is the lead author of best-selling college textbooks, 6 critically acclaimed books for the general public, and children's books, some of which actually were selected by the Storytime from Space program to be read from International Space Station. In today's presentation, Dr. Bennett will give us a foundation we need to speak intelligently about the science behind global warming and show that the solution to this important problem are ones we can all contribute to. And so, Dr. Bennett, the Zoom screen is all yours.
Well, thank you very much. And thank you all for joining us today. Happy Earth Day. I am coming to you from planet Earth, although it might not look like it behind me. This is a wonderful painting of an imaginary planet out on the outskirts of our Milky Way galaxy that I like to sit in front of during my Zoom presentation so I can pretend that I've gotten to travel out there. I am going to share my screen now so that we can get into the presentation. And hopefully right now you can see it. So The title of my talk today is Global Warming, Demystified, answering your questions about the science, the consequences, and the solutions. So what I want to do today is just give you a very brief overview of these ideas so that you'll feel more confident, I hope, in talking about it. If you have questions about the science or consequences of global warming, you'll have some understanding of them, maybe that you don't already have. And we'll also get a chance to talk about how we can solve this problem, which I believe is one of the most difficult problems we face in some ways, but in other ways, a very easy problem to solve. I will point you to this link here, globalwarmingprimer.com. I have a book that this talk is based around called the Global Warming Primer, and it is posted for free online at this web link. So I will refer to that a few times, and if you have more questions that I don't get to today, you'll probably find them answered there at that link. So to get into this topic, the first thing that I want to do is ask this question: what is the future? Because when we talk about the topic of global warming, sometimes there's a little confusion about how far out we're thinking. And I chose this photo to show you because this is kind of the future that I'm thinking about right at the moment, which is just this amazing thing with the Ingenuity helicopter on Mars that's already successfully done one test flight and will be doing more, and the new Perseverance rover that will be exploring Mars. But this is actually a very near-term future right now because this is already happening. So ask yourself, if I were to say to you, what do you envision for your future? What will come into your head? And it probably depends on a lot of different things. But for example, when I've done this with different groups, I find, most middle school students, if I ask that question, they're thinking about the future being high school. If I ask high school students, they're thinking about the future being college, and so on. But when it comes to the topic of global warming, we need to expand our horizons a little bit. When you hear about global warming reporting, you may hear about things like what might happen or what we should do by the year 2030 or 2050. But it's very rare that you hear people talk much farther than that. And that's unfortunate, because if you think about the future, if you're my age, maybe 2050 is sort of the limit of it already. But for today's school kids, for your kids and grandkids, if you're older, the future goes way beyond the year 2050, way beyond the time that we usually hear people talking about when we hear about global warming in the news. And just to give you a sense of that, all you have to do is realize that the average lifespan now is over 80 years. It's very likely that by the end of the century, the average lifespan will be 100 years, which means anyone who's been born in the last 20 years or so, including all of you college students who are out there, you can really expect to still be alive in the year 2100 and beyond. So when we talk about global warming and its effects on us and what we're going to do about it, I want you to start thinking not just about the next 10 years or 30 years, but about the year 2100 and beyond, because for many of you out there, that is your life that you were still looking at that point. And with that, I want to get right into the science of global warming, the first of my three topics: science, consequences, and solutions. You notice here I put also known as climate change. I'm going to use the terms interchangeably. Sometimes there's a slight distinction between them, and global warming referring to the average warming of the whole planet, whereas climate change referring to the idea that different places have their climates changing in different ways. I am an astronomer by training, and so I like to approach this topic from an astronomical point of view, and that's very useful because in this case, actually much of what we know about the science of global warming originated with astronomy. And so I'm going to start out with what I like to call a tale of two planets. And so what I've put up here on the screen for you is the Earth and Venus, and in this picture, they are shown to scale. And what you see right away is that Earth and Venus are the same size within very close amounts. If you were to cut them open based on other data we have about these planets, you'd also find that Earth and Venus are very similar inside, the same basic layering, the same basic composition. And in fact, at least for our solar system, Earth and Venus are about as close to being identical twin planets as it would be possible to be. They're so similar, in fact, there's only one major difference between them, and that major difference is their global average surface temperatures. On Earth, we have this very pleasant surface temperature that works very well for us to live. Venus, you can see, is extremely hot, hotter than a pizza oven. In fact, hot enough to melt lead on its surface. So one of the things I want you to try to do when you're thinking about the science of global warming is sort of approach it the way a scientist would approach it. And in this case, that means, looking at what appears to be a mystery here, which is why would two planets that are in most ways virtually identical twins still have this one major difference between them? And you might think about how you, what you think might be the answer to that. And if you're like most people, your first guess will probably be that the answer is the reason is because Venus is closer to the sun. And it's true that Venus is closer to the sun, but in fact, that is not the explanation for this huge difference in temperature, at least not on its own. And to see why, you can calculate it out, but you can get the idea by looking here at this photo of the Voyage Scale Model Solar System on the National Mall in Washington, D.C., where we've built the solar system at a 1/10 billionth scale. So there's the sun, it's about that big, and that's the sun at 1/10 billionth of actual size. And on that same scale, the Earth and Venus here would be about the size of the ballpoint in your pen. So they're very, very tiny on this scale. And where are they located? Well, there's the sun, there's Mercury, Venus, and Earth are in those two pedestals right there. And so what you'll see is, yes, Venus is closer to the sun, but the way you can realize that that's not enough to account for this huge temperature difference is imagine there was a giant bonfire here at the location of the sun, and then you go stand over by Venus and stand over by the Earth. Well, sure, it's going to be warmer at Venus because it's closer to the sun, but you can see from this photo, it's not going to be that much warmer. Certainly not enough to account for that huge difference in temperature. So if distance is not the explanation for why Venus is so hot, what is the explanation? Now, if we were in a science class, we could go through a lot more hypotheses and testing them out, but I'm just going to tell you the answer. And the answer is something called the greenhouse effect. Most of you have probably heard about the greenhouse effect before. You may even have seen how it works, but in very brief terms, the way it works is that sunlight is coming in and warming up the Earth or Venus or any other planet, and that energy is coming largely in the form of visible light. Some of that visible light gets reflected right back to space, but the rest of it is absorbed on the ground here. And the ground then has to send that energy back to space in a different form. We know it's not sending it back as visible light, because if it was, we'd see the ground glowing in the dark. Instead, the ground is sending the light, the energy back up to space in the form of infrared light, a kind of light that we can't see with our eyes, but we can see with cameras. So these red squiggles represent the infrared light heading back up to space. And what you'll notice is that instead of going straight up, like the visible light goes up or comes down, the infrared light bounces around. And what causes it to bounce around? It's the blue dots. And the blue dots represent what we call greenhouse gases. The three most important greenhouse gases on Earth are water vapor, carbon dioxide, and methane. And what makes them greenhouse gases is the fact that they absorb the infrared light and then they re-emit it in some random direction, making it take longer to get out. And the result of that is, because the infrared light is being kept down at the surface longer than it would be otherwise, it means we get more heat or energy at the surface, in the oceans, and in the lower atmosphere of our planet. Now, remember, I told you I want you to think like a scientist, and one of the things you might think about is, that's a nice story that I just told you about how the greenhouse effect works, but how do I know that it's true? What makes me so confident that there really is this thing called the greenhouse effect, and it really does make planets warmer the way I've just showed you? And the answer is because, number one, we've studied it in the laboratory. In fact, the first measurements of the greenhouse effect in the laboratory were made way back in 1856 by a woman named Eunice Newton-Foote. A few years after that, John Tyndall measured them. Here's a picture of his lab setup. And in fact, by 1896, right, 130 years ago almost, we already knew enough about the greenhouse effect that the Swedish chemist Arrhenius was able to calculate what the effect of doubling the CO2 in our atmosphere, the carbon dioxide in our atmosphere, would be. And kind of amazingly, the result he got with a fairly simple calculation back then is very close to what we get with our most sophisticated climate models today. And so as a result of this laboratory evidence, we know exactly how the greenhouse effect works for all the different gases in our atmosphere and how much of different forms of light they absorb and let through. Now, one of the things you may know when you think about science is there's always a question: does what we see in the laboratory translate to the real world? And in this case, we can test that also by using real worlds like the Earth and Venus, planetary evidence. So what we do is based on our laboratory measurements of the greenhouse effect, we can calculate what we would expect the temperature of a planet to be and compare it to what the actual temperature is. And what we find is if we include the greenhouse effect in our calculations, we get the right answers. If we try anything else, we don't get the right answers. So that confirms that what we observe in the laboratory for the greenhouse effect is in fact operating on planet scales as well. And one thing that's very interesting in this process is that when you calculate what would happen on a planet like Earth without the greenhouse effect, and here's the actual calculation right there in this picture from another book of mine, The Wizard Who Saved the World. If we did not have a greenhouse effect on Earth, Earth would be too cold for life. Instead of having that nice, pleasant average temperature of close to 60 degrees Fahrenheit, the average temperature of Earth would be below freezing without the greenhouse effect. And that lets us go back to our tale of two planets and summarize it. So the reason that we have this nice, pleasant temperature on Earth instead of being frozen is because we have enough carbon dioxide in our atmosphere to make our planet livable. In other words, the greenhouse effect, due to the naturally occurring carbon dioxide in our atmosphere, is a very good thing for us and for life, because without it, we wouldn't be here. What's going on Venus? Well, on Venus, it has about 200,000 times as much carbon dioxide in its atmosphere as Earth does. So back to that picture of the greenhouse effect, imagine 200,000 times as many blue dots, and that's going to make the planet much, much, much warmer. So what I like to think of when we're talking about the greenhouse effect is the greenhouse effect is a very, very good thing for life on Earth, but Venus is proof that it's possible to have too much of a good thing. And that is where the science of global warming begins. We have absolute proof from Venus that more greenhouse gas really means warmer temperatures. That starts to make scientists concerned, because scientists have been measuring the amount of carbon dioxide in our atmosphere since the late 1950s. And this is a famous graph that you may have seen before, showing the change in concentration of carbon dioxide from the 1950s to the present. And what you see very clearly is that it is rising significantly. The units over here are called parts per million, which basically means out of every 1 million molecules of air, how many of them are carbon dioxide. And you can see, first of all, it's a relatively small compared to 1 million. Carbon dioxide is a trace gas in our atmosphere. There's not very much of it, but because it's a greenhouse gas, it's very important. Most of our atmosphere is made of nitrogen and oxygen, and they are not greenhouse gases. They do not affect the infrared light going back up into space, and therefore they don't have an effect on our planet's temperature. But the carbon dioxide does. And back in the late 50s, it was around 315 parts per million, and we're now up close to 420 parts per million. That is a substantial rise. Now, one of the things that you might be wondering is, how do we know that this carbon dioxide is being caused by us humans rather than some natural effect? And I won't go into details, but if you go to my website, globalwarmingprimer.com, and look up the primer or look in my book, you'll see we have 4 very clear lines of evidence that all prove conclusively that this rise is due 100% to the burning of fossil fuels and related human activities. You might also be wondering, well, what is the natural carbon dioxide level like? Does it ever fluctuate naturally? And to answer that question, you would want to know, what was the carbon dioxide level like further in the past? And you might at first think that would be very difficult to know, since nobody was measuring it before 1958. However, it turns out there's a lot of different ways we can measure the carbon dioxide level going further into the past. One of the best ways is by drilling these ice cores down in Antarctica. So what the scientists do, as you can see in these photos, is they drill down and bring up a tube of ice with the drill. This is just one small section of one of those ice cores. The longest ice core that's ever been drilled went down 2 miles into the ice. And you might wonder, so what does that tell us? Well, to answer that, you have to think about, where did the ice in Antarctica come from? And the answer is, long time ago, snow was falling on the dry Antarctica. And over time, because it's cold down there, the snow kept piling up year after year after year. And in fact, when you look into these ice cores, you can see layers in them, almost like looking at tree rings, that you can count back how many years ago you're looking at in the layers. And in these layers, there's bubbles of air that got trapped at the time the snow fell. So scientists can go in there and measure what was the carbon dioxide concentration at that time. And remember, I told you the deepest ice core went almost 2 miles down. And it turns out, when you count through the layers there, that means they brought up snow that fell all the way as far back as 800,000 years ago. And actually, they're working on an even deeper ice core right now. And this graph shows you the results. This is the 800,000-year record of carbon dioxide in Earth's atmosphere. So over here, you can see the scale is thousands of years ago. So this is the present 0. That's 100,000 years ago, 200,000 years ago, and so on, back to 800,000 years ago. And what do you see? Well, the first thing you see is that the carbon dioxide concentration varies quite a bit. And this is all natural variation, because we weren't around to be causing it. However, you'll notice that this natural variation has been between about 180 parts per million and 280 parts per million. In fact, in the year 1750, kind of around the beginning of when humans started to use a lot of fossil fuels, it was 280 parts per million, but it has shot up since then. We have to zoom out to see the most recent part, again, to almost 420 parts per million. And if you extrapolate this upward, you'll see that means we're on track to be at double that pre-industrial value. So up at 560 parts per million, way up here, only in about 50 years or so, triple that by the middle of the next century, and so on. And that brings me to the summary of global warming science. You'll often hear people say global warming is very complex and the climate is very complex. And it is. But the basic idea is very, very simple. So simple that I like to summarize it with what I call global warming 1, 2, 3. What is the 1, 2, 3? Well, here's number 1. As we've seen already, it's a fact that carbon dioxide is a greenhouse gas that makes Earth warmer than it would be otherwise. I've already shown you how we know that through the laboratory measurements and the planetary evidence. Number 2, it's also a fact that by using fossil fuels, coal, oil, and gas, we are adding more carbon dioxide to the atmosphere. I've shown you the graph of what we are doing, and I've explained how we know that it is due to us and not due to any natural factors today. And if you put number 1 and 2 together, number 1, more carbon dioxide means warmer temperatures. Number 2, there's more carbon dioxide. Then number 3 is pretty obvious. It's going to get warmer. And that's it. Global warming 1, 2, 3. That is the basic science of global warming based on very simple physics that we've known about since the 1850s. There is 100% certainty that adding more carbon dioxide to the atmosphere should make it get warmer. And that is exactly what's happening. You can see here on this graph of global average temperatures going back to the 1880s. The zero line is the 20th century average temperature. That the trend is clearly upward. It is, in fact, getting warmer, just as we expect. And you might ask yourself, if it's so simple, why do so many people, and in particular so many politicians, have so much difficulty understanding this very simple science? And I might just ask you a quick quiz question so you can think of your answer, maybe even post it to each other in the chat. Who do you think was the first major global leader to speak out on a major global international stage and say, basically, hey, this is simple, 1, 2, 3, we've got a problem here? And here's the answer. It was British Prime Minister Margaret Thatcher in 1989, delivering a speech to the United Nations. This is what she said. What we are doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways. And you can see that in this statement, she's basically just restated the global warming 1, 2, 3 ideas, that we know more greenhouse gas is going to make it warmer. We know we are adding more greenhouse gas to the atmosphere, and that is going to create problems for us. And this is something she said more than 30 years ago. And I think it's also worth noting that sometimes you hear that global warming is somehow a political issue, a liberal thing or something like that. And yet here it is, the first major global leader to speak out on it was one of the founders of modern conservatism. And by the way, if you want to see the whole speech that she gave, it's posted, there's a link to it on my globalwarmingprimer.com website. I also want to very briefly address, okay, given that, how can some people still be arguing that it's not real? And so in my global warming primer, again, you can read it for free on the website. I have a whole chapter that goes through the common skeptic arguments. I'm not going to go through those here today, but I just want to focus on 2 of them very, very briefly. The first is, sometimes you might hear people say it's the sun causing global warming. But here, this one graph, along with several other lines of evidence, prove conclusively that it is not the sun causing this. In this case, we see the temperature change on Earth going back to 1880 and the amount of sunlight from the sun, how the sun is changing since 1880. And you might believe during this part of the graph up to about 1960 that the sun was linked to the changes. But since that time, the sun and the temperature have been going in opposite directions. So that proves it cannot be the sun. The second really common thing you may hear is, well, the climate changes naturally all the time, so why worry? And the answer is because, yes, the climate does change naturally, and that should actually make us even more worried. This graph shows you the same in blue, the same graph I showed you previously of the carbon dioxide concentration over the past 800,000 years. And the red curve is the temperature on Earth at those times, also measured from the ice core samples. And what you'll notice is the 2 curves line up almost perfectly. And there's a reason for that. The reason is because 1, 2, 3, more carbon dioxide means higher temperatures, less carbon dioxide means lower temperatures. So what we see is exactly what we know we should see from the global warming 1, 2, 3 basic science. Why should this give us so much concern? Because you'll notice one thing that's not clear on this scale is there's always a lag time between the response of the atmosphere to changes in carbon dioxide. There's also some complex feedbacks that I won't get into now, but maybe we can talk about that in the Q&A. But the point is, we were already at about one of the highest temperatures of the past 800,000 years before we started adding all this carbon dioxide to the atmosphere. And we know there's a lag time in when the temperature should respond. So the fact that the carbon dioxide has gone up so much should certainly make us concerned that the temperature may follow also by a similarly large amount. I want to turn to the second part of my talk, which is the consequences of global warming. I hope I've convinced you now that the basic science is very simple and clear, and we know that global warming is going to occur and is occurring as expected. So what are the consequences that we can expect from this? I'm going to break them into 5 basic categories. The first is regional climate change. The whole Earth is warming up, but that's not the big concern. The big concern is how that affects different places. So by regional climate change, we mean the idea that different places may warm by different amounts. And this is a really wonderful map that NASA has put together showing you global average temperatures in 1880 to 84 right now compared to the 20th century average for each location. So a place that's red at that time was warmer than its 20th century average. A place that's blue was cooler than its 20th century average. And now I'm going to play the video and you can see time running by down here. And you'll notice that over time, some places are warmer than average, some places are cooler than average, but it kind of looks pretty random as we go all the way up into even the middle of the last century. But as you keep watching, notice that it starts to not look so random anymore. And by now, you see very clearly that the whole world is warming, but some places are warming a lot more than others. And in particular, the Arctic is warming much more than others. And this regional climate change has many other consequences that I won't go into right now, but I want to show you just one that's particularly interesting and you've probably noticed. This is a graph from James Hansen, famous climate scientist, in which he's plotted for the whole Northern Hemisphere, he's averaged out everything to make a bell curve of summertime temperatures, showing you that most days are kind of what we call normal, and some days are cooler than normal, some days are warmer than normal, or extremely hot, extremely cold for summertime compared to the summertime average. And this is the graph for the period 1951 to 1980. And now you see the same graph for the period 2005 to 2015. And you'll notice the whole graph has shifted to higher temperatures so that what we used to call a hot summer day is our new normal. And you've almost certainly noticed that wherever you live, there are more hot summer days than there used to be. And that's just one of many consequences of regional climate change. The second category of consequence I want to focus on is an increase in storms and extreme weather. And I want to just explain this very briefly because, again, it's not hard to understand the basic idea. Remember what global warming is doing or where it's coming from. It's coming from that extra heat and energy being trapped down in the atmosphere and oceans. And you might ask yourself, what causes storms and other extreme weather events? And the answer is energy. So as we add more energy to the atmosphere, we expect to get more extreme weather events. And we're seeing that with hurricanes, with dry spells that can lead to wildfires. Here's a graph showing the increase in extreme weather events over time. It's very, very clear. And in fact, one of the surprising things to a lot of people is when I say extreme weather events, that means extreme weather events of all types, including extreme winter storms. So when we get some of these really strange winter storms, I know you had some there in the Boston area recently, that's also an expected consequence of global warming because it's the extremes that we expect to see more of. The third major consequence of global warming is the melting of sea ices up at the Arctic Ocean. Remember, the Arctic is warming the most, and as a result of that, we're getting less ice coverage in the Arctic Ocean. That, in fact, may be tied to this thing you might have heard about in the news called the polar vortex that may explain the details behind some of that weird winter weather we've experienced in recent years. But one of the most concerning things about the melting of sea ice is that it amplifies global warming. And the reason is fairly simple, because ice reflects a lot of sunlight. It's bright. Water absorbs more sunlight. And therefore, as we get less ice coverage in the Arctic, more sunlight is absorbed by our planet. And that just amplifies the other warming that's going on due to the carbon dioxide and the increase in greenhouse gases. The fourth major consequence is rising sea level. Now, you might wonder why I didn't mention that with the melting of sea ice, and it's because sea ice doesn't affect sea level because it's already floating. And so when it melts, it doesn't change sea level. However, sea level rises due to two other effects of global warming. One is that as the oceans warm, the ocean water actually expands a little bit. The expansion of water with temperature is so small that you'd never notice it in a glass of water, but in the entire depth of the oceans, it's already added about a foot to sea level over the past century, and will almost certainly raise sea level by another foot or so by the end of this century. On top of that, we have a rise in sea level being caused by the melting of glacial ice on mountain glaciers in Greenland and in Antarctica. When that ice melts, it ultimately runs out into the oceans and causes sea level to rise. And you can see, for example, here's a map of the southeastern US, showing you the red areas that would be flooded by a 1 meter rise in sea level, which is what many scientists think is likely by the end of this century. A 6 meter rise would flood even more. That's not likely by the end of this century, but perhaps not that long after it. And you might wonder, if we continue to let the world warm up, well, eventually we would melt all the ice in Greenland and Antarctica, which would cause sea level to rise by more than 200 feet. So think about that wherever you live, what a 200-foot rise in sea level would mean. And even though that wouldn't happen for a couple thousand years at least, it's an interesting vision to put in your head of imagining our descendants a couple thousand years from now needing deep sea diving equipment to visit the ruins of today's major coastal cities. And finally, the fifth major consequence of global warming is called ocean acidification. This is the one that you hear the least about, but in some ways it may actually be the most serious one. It's the idea that as we increase the amount of carbon dioxide in the atmosphere, not all of that carbon dioxide goes into the atmosphere. Some of it is absorbed in the oceans, and there it turns into acid and makes the ocean water more acidic, which is affecting our fisheries, coral reefs, and other things that a lot of people depend upon for their livelihoods. And so at this point, I want to turn to the last part of my talk, which is on solutions. And I think if you think about it, what I've been talking about, I hope that you will now understand why Greta Thunberg says, I want you to panic. I want you to feel the fear I feel every day. Because once you understand the basic science and consequences of global warming, it is a very scary thing. It is a very worrisome thing for our futures. But you can't stop with fear. You have to keep reading what Greta says. Notice her last line. And then I want you to act. And the reason she wants you to act, and the reason we should all want to act, is because as scary and as serious as this problem is, it is a solvable problem. Why is it a solvable problem? You know, if you're a teacher out there, you've probably told your students that the first important key to solving any problem is to understand it. And in this case, we understand the problem really, really well. It's as easy as 1, 2, 3, like we've already talked about today. We know the problem is being caused primarily by the burning of fossil fuels, and therefore the solution is also very simple. Stop doing that. That's it. Stop the burning of the fossil fuels and the other things that contribute to global warming, with that being the biggest one. Stop it, and that will solve the problem. Now, of course, it's easy to say, stop burning fossil fuels, but we like the energy we get from them. And therefore, if we're going to not use fossil fuels anymore, we need to have some alternative to get our energy from. But it turns out we know how to do that. We already have all the existing technology that we need to replace all our current use of fossil fuels and still have just as much energy for our lifestyles as we have today. We don't need to sacrifice anything in our lifestyles. What are those technologies that we have? Well, three basic things. The first is energy efficiency. You might not think of efficiency as a source of energy, but it really is, because if you can get the same benefit for less total energy and less total cost, then that's just like having a new source of energy. The second technology is renewable energy, wind and solar energy, for example, hydropower also. And those have tremendous potential. For example, the amount of solar energy reaching the Earth is 20,000 times what we use as a civilization today. So we'd only have to tap 1/20,000th of all the solar energy coming in order to replace all our energy use with solar. And we have other renewable options too. And the third technology is nuclear energy. And I know lots of people have lots of opinions about nuclear energy, but it is clearly safer and cleaner than fossil fuels by any measure. The toxic waste from a nuclear power plant produced in an entire year is what we get from 1 hour of a typical coal power plant. We also would then have no more air pollution, which would save some 10 million pollution deaths annually. And nuclear power, just like renewables and efficiency, does not emit any greenhouse gases. So I'm not going to tell you which of these we should use, but in some combination between these existing technologies, again, if we wanted to, right now, we could completely solve the problem of global warming by switching away from fossil fuels to these technologies. And there's even more to come in the future. People are working on advanced carbon neutral biofuels, which we can use even in existing airplanes. And then you don't have to worry about the impacts of your flying anymore and on ships. Some of these can even remove carbon dioxide from the air as they're being grown, these biofuels. Solar energy from space is one of my favorite ideas. You put your solar panels, one of the difficulties with solar energy is it only works when it's daytime and when it's not cloudy. But if you put your solar panels up in space, it's never daytime and it's never cloudy. Excuse me, it's never nighttime and it's never cloudy. And so you can collect energy all the time, beam it down to Earth. People are working on that also. Nuclear fusion, which is a technology different from our current nuclear reactors. It's the way the sun generates energy. And the fuel is hydrogen, which you can get from ordinary water. And in fact, a simple calculation will tell you that a single kitchen faucet, if you just ran the water and extracted the hydrogen and fused it, could provide the power needed for the entire United States. An incredible source of energy. Again, one that we don't have yet, but people are working on. Technologies for removing carbon dioxide from the atmosphere so that we can actually undo some of the damage we've already done by lowering the carbon dioxide level back down from its current 420 or wherever it may be heading to in the future, back down to some more reasonable level. James Hansen's group has calculated that 350 parts per million would be a good target. And I just want you to keep these ideas in mind for a little bit, because we're going to come back to them in the context of thinking about the future, the way we talked about at the beginning of my presentation. And so finally, if we already have the existing technology to solve this problem, and we've got more technologies coming online, why haven't we just fixed it already? Why is this still a problem? What's stopping us from solving this problem? And I put this disclosure on the screen here because I would argue that up until now, everything I've told you is an indisputable scientific fact. But now I'm going to get into some economics and policy issues where you'll be hearing my opinions. So let's look at what the economists say about fossil fuels. Well, you'll often hear that fossil fuels are cheaper than these alternative sources, but that's only cheaper at the time you buy them. If you count the socialized costs, the cost that we don't pay at the time we produce these fuels, but instead that gets spread out across society over time, it turns out there's a lot of them. There's health costs from air and water pollution caused by fossil fuels. The National Institutes of Health says that's at least $120 billion a year in the United States alone. And remember those 10 million air pollution deaths a year that occur worldwide. There's the cost of the defense of our oil supply and the international flow of these fossil fuel energy sources. There's subsidies and tax write-offs. There's the dangers posed by the fact that a lot of the regimes and groups that have caused us problems in recent decades have gotten their money from us buying their fossil fuels, their oil from them, the environmental damage and so on. And in fact, the total estimated subsidies for fossil fuels by both conservative and liberal economists, including the International Monetary Fund, it's estimated that we subsidize fossil fuels by $1 trillion per year in the United States and globally by about $4 trillion per year. So what has been stopping us, in my opinion, is we think fossil fuels are cheaper when in fact, once you include these costs, they're not. Because if you spread that out over the cost of fossil fuels, you'd find that, for example, with gasoline, instead of being $2 or $3 per gallon, once you include these costs, it would be more like $10, $15 per gallon. In other words, fossil fuels are being subsidized and are artificially cheap. And I think that's the reason we have not already solved the problem. So what do we do to correct that? Well, if you ask any economist, liberal, conservative, it doesn't matter. How do you correct for these kinds of socialized costs? You may hear economists refer to these with the fancy word externalities. And the answer is you charge that cost into the price with a carbon tax, a carbon fee. And you may think, okay, well, a carbon tax, that's never going to fly politically. But in fact, it turns out it has bipartisan support. There's already been bills, bipartisan, introduced in Congress to do this if you make it revenue neutral. In other words, you charge the carbon tax, but the government doesn't keep that money. It returns it back to the taxpayers in the form of dividend checks or something like that. That is the plan advocated by a group called the Citizens Climate Lobby, also by a group of former Republican officials, also by a group of college student leaders on the environment. So it can certainly be done. Again, this has already been proposed in Congress. And personally, to me, this is the most obvious way to solve the problem of global warming. Because if we put that carbon tax on, then we will pay the true cost of fossil fuels. And as soon as we're doing that, everyone will realize that the other sources are actually already cheaper, and they'll become even more cheaper as market incentives drive those costs downward. I'm putting up this picture here from the Republican official group that I mentioned, and they wrote this about the conservative case for carbon dividends, the idea that putting on this tax and dividend plan is their new climate strategy that can strengthen our economy, reduce regulation, help working class Americans, shrink government, and promote national security. And it's so almost magical sounding when they say that I want to briefly break it down for you. How does it strengthen our economy? Because remember, when you include the cost of those subsidies, we are paying more for our current energy than we would be paying if we switched. So switching actually saves us energy money, which strengthens the economy overall. They say it would reduce regulation. Why? Because a lot of the reasons that we have regulations about greenhouse gases is because right now they're artificially cheap. If they weren't artificially cheap anymore, we wouldn't have to have all those regulations. Help working class Americans. You may wonder, how does a tax help working class Americans? Because of the dividend. On average, working class Americans would get more money back in the dividend than they would spend on the tax. Shrink government and promote national security because we don't have to have as many regulations, letting the market deal with this, and promoting national security because we don't have to worry so much about oil revenue going to groups that may not have our best interests in mind, and so on. So I want to now return to what we started with, the tale of two planets, only now it's a tale of two futures on one planet. And so one future is if we do nothing, we just keep going the way we are. And I hope that I have convinced you that this really is an existential threat to modern civilization. And just to be clear on what I mean by that, I'm not saying we're going to kill off life on Earth. We won't. I'm not saying we're going to drive humans extinct. We won't. What we are threatening is the civilization that we have come to enjoy, the prosperity that we've come to enjoy. That will not be able to continue if we let this problem continue. But you may often hear that the alternative to that is we get by somehow. But in fact, I want you to now think about those future energy sources we talked about. Imagine it's the year 2100 now, when today's college kids and younger kids will still be alive, and most of us will have kids and grandkids still alive. In the year 2100, let's say we have solved this problem by replacing fossil fuels long ago, back as 2030, 2050, we've stopped using fossil fuels. Then we develop technologies to pull more carbon dioxide out of the atmosphere and bring us back down to 350 parts per million, undoing the damage we've already done. And we now have solar energy from space, or nuclear fusion, or some other source that gives us essentially unlimited, clean, cheap energy for the world. That is an incredible future, because with all that energy at low cost, we could eliminate poverty on Earth if we put it to work properly. We could eliminate problems with fresh water because we have plenty of energy to desalinate ocean water. We could stop destroying parts of the Earth for mining because we could just go get our minerals that we need from the moon, and so much more. The future in the year 2100 is not a choice between this threat and something barely getting by. It's a choice between this threat and something that will make our Mars Perseverance rover look like nothing by that time, because we will be doing so much more. The future of a post-global warming world is possible. It is real. All we have to do is act in the right ways. And with that, I'm going to bring this to a close with a couple of last thoughts. This is one of my favorite cartoons from Joel Pett down in Kentucky, showing you sort of the idea that we get all these other benefits when we switch away from fossil fuels, even if you still don't believe me that this is a serious problem. It's a win-win, whatever you believe. And finally, I know there's still a lot of debate about this. I hope that those of you who might not be convinced or haven't been convinced, maybe I've helped change your minds about that. But in this world today, it's easy to think that we're all so polarized that we can't agree on anything. But there is one thing that I believe we all agree on, from the furthest right to the furthest left of politics. The one thing we all agree on is we all want a better world for the future, for our kids, for our grandkids. And so I want you to imagine this. I want you, whatever your political beliefs are, to imagine writing a letter to your grandchildren that you'll write it, we'll seal it in a time capsule, and they will open it 50 years from now. Why 50 years? Because on average, 50 years is the age difference between you and your grandkids, whether you have them already or not. In other words, on average, 50 years from now, all of us would have grandchildren, if we have any, that are exactly the same age we are today. So you write this: dear grandchildren, as I write this in 2021, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you are my age. I have examined the evidence and I have decided to, and you fill in your decision. Hope your world is a good one. Love, you. And ask yourself, what will your grandkids think of you when they open this letter 50 years from now? And I think if we all think about the problem in this way, we can all come to good decisions about what we're going to do to help solve the problem of global warming, because again, it is solvable. And then I'll close with a quote from another famous conservative, Ronald Reagan. What is a conservative after all, but one who conserves, one who is committed to protecting and holding close the things by which we live? This is our patrimony. This is what we leave to our children, and our great moral responsibility is to leave it to them, either as we found it or better than we found it. And that's the end of my talk. I'll remind you, if you still have questions, you can go to my global warming primer for the adults, globalwarmingprimer.com. For the kids, I have my book, The Wizard Who Saved the World, which you can hear being read from the space station at storytimefromspace.com, or see more about at bigkidscience.com. And for middle school and high school students, I have a free online curriculum for climate change at this link, bigkidscience.com/climate change, which takes you to a chapter in my Earth and Space Science curriculum. That is actually designed for several weeks of study in middle school or high school. Any of you teachers out there are welcome to go to that. Again, it's free. Those are all of my other books, my children's books, all of which have been read from the space station, my books for the general public and college. I also want to point out a free app that you can download for learning about eclipses called Totality. So iOS, Android, you can download that right now, learn about the eclipse that will be passing across the United States in 2024. And again, the free Earth and Space Science curriculum and global warming primer. So I will stop there. Thank you very much. And we'll see if we've got any questions coming in.
Absolutely. Well, thank you, Jeff, first of all, for such a clear presentation. I like how you presented in such a way that we could all access it, but you didn't water it down. You made it, again, accessible, but you treated us as adults, as we should be treated. The other thing is that also, thank you for this positive ending where you really open up to us as the people who can make a difference in some way or another, this encouragement of thinking about what we would say to our grandchildren that we contributed to solving this problem, to create a better future. So I really want to encourage everyone to start posting their questions or comments. Those are welcome as well in the Q&A. I know there is already a question. I think you can see it. I think you've been addressing how we can stop climate change. I don't know if you want to add anything more at this point.
Sure. So, I think I've mostly addressed what I would have to say about that. But one thing that I didn't talk about too much that I know a lot of people ask about in terms of this topic is, what about other things besides fossil fuels, like cement production, like methane from rice paddies and from cattle and so on. And those are related things. We have to deal with those as well. But if we have those energy resources and we keep working on it, we can solve all those problems. People are already working on ways of making cement without the release of carbon dioxide. People are actually working on genetically modified cattle that would not release methane anymore, or cultured meats that you may have heard about that would not lead to greenhouse gas. So there are ways to deal with all these things. We just have to decide we want to do it. And again, from my point of view, I think the best way to make this happen quickly is to put on that carbon tax in a way that everybody can support with that citizens climate lobby type of plan. But you may have other opinions. The important thing is that we make that switch away from fossil fuels as quickly as possible. And that gives us time to then figure out all the rest of the things that we need to deal with.
Yeah, I mean, I've been reflecting a lot. You provided us with a lot of ideas from a technology point of view and alternative energy sources that we have. I think that the big hurdle here is that how do people really come to terms with the fact that, yes, it's a shift? I mean, the word change, no matter which direction we are going, people tend to be, most people are not walking into change easily. And so, yes, it's giving everyone a view of the future that is a better future. I really like that. But how do we really deal with much more of this public, I'm sorry, public communication to the public, right? Or anyway, public perception of the issues. It's more a psychological approach, right?
Yeah, well, we have to understand it, and we have to help people understand the problem, and we have to help them understand it in a positive way. Again, that this is not something that's going to hurt us to make this change. It's going to make our lives better to make this change. Mm-hmm. And there will be some people who will have difficulties in the short term, particularly if you're a fossil fuel worker. But that's why we have ways of dealing with that. We need government policies that will help people who need that kind of help. But we do have to get serious about the problem. And I'll just tell you a very brief story from one of the times I did this talk at a retirement home. And I asked people how long did they think it would take for us to make this change, if we were serious about it. And a few people, put up their hands and said, 20 years, 30 years, 40 years. And then this 95-year-old man put up his hand and he said, no, 3 years max. And I looked at him, I was like, I've never heard anybody say we could do this in 3 years max. He goes, well, that's because you didn't live through World War II. And in World War II, we changed the entire economy of the United States in less than 3 years because we had to. We knew it was serious. We had to do that. And therefore, we did. He said, all we need to do is be just as serious about this problem, and we can make the change very, very rapidly. And I think he's right.
Yeah, that's a very interesting analogy, though it took a little bit of time to the United States to agree to get into that.
Yeah. I see a question has come in about deforestation and reforestation, which is
right.
An excellent question. So trees are basically made of carbon that they get from breathing in carbon dioxide. And therefore, trees pull carbon dioxide out of the atmosphere. When we cut them down or burn them, their carbon dioxide goes back into the atmosphere. So deforestation makes global warming worse. Reforestation helps make it better by pulling carbon dioxide out of the atmosphere. So yes, these are real problems that we need to deal with. We need to try to stop all the deforestation. And again, there's a lot of things to think about in how we do that. One is, how do you help people in areas where they're currently doing the deforestation? Why are they doing that? And what can we do to help them change that? So for example, with the Amazon, a lot of that is being done either for cattle grazing or for mining. So if we can come up with alternatives to those, then we can help not have to have so much of that done. And if we can help those people get jobs in other ways, whether it's through ecotourism, through other things, we just need to work on these things together as a globe. I always like to remind people, global warming is a global problem, and therefore it needs global solutions.
Also, you may want to see in the chat, or I can read it. It's a very important comment. I think introducing these topics like global warming right from an early age through the school system is going to have huge impacts in terms of awareness about global warming. What is your experience when you give these presentations to very young audiences?
Young kids seem to have a pretty good grasp on the seriousness of this problem already. I think in part because it's their lives that are going to be the most affected, because they're still going to be alive in 2100 and beyond. And I think because of the young people's movement, Greta Thunberg and all the others who have really helped awaken people to this. But again, I think we do need a better job of helping to teach what's actually behind this. What is the science behind this, and how do we deal with it? And in particular, we have to make clear this idea that I've been talking about of a post-global warming world. We're not looking at a future where it's not a choice between bad and barely. It's a choice between bad and awesome. And that post-global warming awesome is the future that our kids can live in, today's kids can live in, if we all act right now and help make that possible for them. Sometimes I'll tell some of the younger kids, it's great if you focus on this problem, but I'm hoping it'll be solved by the time you're ready for your career. And therefore, you should be thinking about what you're going to be doing in this post-global warming world.
Yeah, absolutely. I mean, I wanted to recognize here that over the past week, you gave 3 presentations to young audiences in the middle and elementary school level, talking exactly about this topic. So you really have a direct experience of what it means to introduce these issues, but the solutions as well to young audiences. Just going to see if anyone has any further questions or comment. Perhaps not. I know I have a lot that I would like to keep talking about, but I know we will have other opportunities to have these kind of conversations. Maybe would you mention briefly about the initiative, of Astronomers for Planet Earth? I think it might be of interest.
So as I think you probably figured out during this talk, I am an astronomer by training, not a climate scientist, but this topic actually, as we talked about with Earth and Venus, sort of arose from astronomy. In fact, perhaps the best known climate scientist, James Hansen, actually started out studying the planet Venus before he turned his attention to focus on climate science and Earth, because that was what really got his attention for it. And partly because it is an astronomical topic, and partly because we're all scientists and need to be focused on it, there is a group that has started called Astronomers for Planet Earth that now has, I think, getting close to 1,000 members around the world of astronomers who are using our sort of podium, if you wish. People like black holes and stars and galaxies, so we can also then talk about climate change. And so that's what Astronomers for Planet Earth is doing.
Right, and if for people who are going to or already following the activities of the McCullough Center, or yours, follow us on social media, you will probably see more about this initiative. We as an organization, we are members of Astronomers for Planet Earth, and I know myself and Mary McDonald, our planetary manager, are individual members of this initiative. So we will keep everybody informed about the activities that Astronomers for Planet Earth are working on, and everyone is welcome to go to their website. Okay, just Google Astronomers for Planet Earth, and you will find there are several videos that are very helpful to introduce the topic and so on. All right, well, I think this brings our presentation to an end. Again, I want to thank you again, Dr. Bennett. And I see, sorry, in the chat, just a reminder that you can find a recording of this event and our previous event on our website. But again, I want to thank Dr. Bennett for this presentation, the past presentation, for really being part of our festival in a way that no other speaker has been this year. We really appreciate that.
Thank you very much for inviting me.
Absolutely. And thank you everyone for joining us today, and keep following the festival's activity and the McCullough Center activities. And thank you for posting also the website for Astronomers for Planet Earth. Thank you all and have a wonderful night.